y'all doing? My name is Matt, and it's my privilege to introduce Phil and Ethan and their research, which is synthesis of 3,5-diisopyl-delta-2-diisopyl.
Hi, my name is Phil, and I'm Ethan Bodak, and for the past 6 weeks we have been working on synthesizing 2,3,5-delta-2, or 3,5-disubstituted-delta-2 isoxazolines. So isoxazolines are a series of drugs known as MIF inhibitors, and MIF, or macrophage migration inhibitory factor, is a pro-inflammatory cytokine, so it causes inflammation in the body. And the way it does that is it produces these proteins that go out to the different sites in the body, and those are the sites where inflammation arises. So MIF is not a good thing, and that's how isoxazoline stops it. So isoxazoline binds to the MIF cells, and it blocks the production of the proteins that cause inflammation throughout different body parts. And so because the proteins are blocked, they can no longer attack the pancreas and different body parts. And what happens particularly when they target the pancreas is it causes inflammation. And when that happens, the inflamed pancreas loses control of the insulin levels, and so that's where the type 1 diabetes cells have their issues and stuff. And so the sugar levels are in the body are reduced. And the effect of these being blocked with inflammation in the body throughout the body comes down because there's no protein.
So current research suggests that the best, or one of the best ways to synthesize these isoxazolines is through a 4-step process. The first step being taking a Grignard reaction and reacting PN-aldehyde to form an alcohol with the functional group 3-butane-1-alcohol. And then the second step is an oxidation reaction of that alcohol to form a ketone with the functional group 3-butane-1-alcohol. The third step is reaction to form an oxime. So we take that ketone and treat it with hydroxylamine to form an oxime, and then the oxime is reacted with a metalloid and cyclized to form that isoxazoline ring.
So our goal for the project was to produce 2 different isoxazolines, one being nickel catalyzed based and the other being palladium catalyzed based. And so when we're doing this, we also wanted to find out if isoxazolines can be produced in mass, as well as if we can produce them at a cheaper cost, because currently it's extremely expensive to make isoxazolines, as well as to buy them, because the pharmaceutical companies and stuff, they raise the price, making them more expensive to buy. And then we also wanted to produce isoxazolines at higher yield, because currently there are research studies being focused on isoxazolines, but they're not being produced at high enough yields, like to be produced to work well in the body. So we were trying to produce the isoxazoline at a cheaper cost, as well as a higher yield, so we had a better isoxazoline.
So our process was fairly similar to what the research suggested. We started with that starting material, PN-aldehyde, reacted it with allyl magnesium chloride in tetrahydropyrin as a solvent, and that got us this alcohol with the functional group 3-butane-1. So this reaction had to be anhydrous, so we did it under argon gas to ensure that any air or water molecules couldn't get into the reaction and potentially tear apart the product. The allyl magnesium chloride is very reactive, so we added that slowly. One, because if we added it all at once, it would just destroy the whole reaction and sizzle and end in a big bang. And also because we didn't want our products to be destroyed. So what this whole reaction did was take this carbon chain off of the PN-aldehyde and lengthened it by a couple carbons. You can also see that it broke this double bond to the oxygen and the carbon and formed the hydroxyl group. Oh, and this is the setup for the reaction. So we had the argon gas inserted through the top of the needle, and the flask was stoppered to ensure that no water would get in.
So here we have the oxidation reaction, which was the next step. And so what we did is we took the alcohol that we just created, and we added pyrrhodium chlorofluorate and magnesium sulfate. and in dichloromethane. And what happened was we did the reaction, and the magnesium sulfate was used to smooth out the reaction, and the dichloromethane kind of acted as a solvent. And so with the reaction being smooth, it keeps it from running away, kind of like the alcohol from the reaction. And so what we did is we removed the hydrogen from the hydroxyl group on the alcohol, and you can see that here. This hydrogen broke up the oxygen, leaving a double bond like here, and it bonded to the carbon over here. So this double bond carbon to the hydrogen. And then here we have a picture of the reaction before. This is with the alcohol, pyridine, chloride, the magnesium sulfate, and the dichloromethane. And here's what the reaction did after running a run from 30 to 45 minutes. And this color change indicated that the reaction ran fully.
So then the third step was that reaction to form the oxygen. So we took the ketone that we had just made, reacted it with hydroxylamine hydrochloride and sodium acetate trihydrate. And what that sodium acetate did was because there's hydrochloric acid in the hydroxylamine hydrochloride that could potentially break down our product, we added that to smooth it so that that didn't happen. We also used a 50-50 ratio of deionized water to ethanol as our solvent for the reaction, and that formed this oxime over here. So the reaction had to be heated, and one of the reasons for that was because we had a condenser bowl on top of the reaction flask. And we waited until we started to see some solution drip off that condenser bowl, and that would indicate to us that the reaction had gone to completion. And what this did was form the base for the isoxazyl ring. So you can see over here on the oxime this kind of semi-ring over here. Well, that ring is eventually going to be cyclized and connected to form a complete isoxazyl ring.
And so after we formed the oxime, we did a nickel catalyzed cyclization. And so what that means is we took the oxime and we added nickel 2 chloride and copper 2 chloride in ethanol, and we ran the reaction through. And what happened was So the copper 2 chloride oxidized the nickel, which means it keeps the nickel 2 from going to nickel 1 or nickel 3, because the nickel 2 is ideal for cyclizing and oxidizing. The reaction was also anhydrous, which we didn't do another argon gas, but we did dry out all the chemicals and products we used. So we dried them out in the oven overnight at 105 degrees Celsius. And we also used tools and stuff that we knew were clean and dry. And the reaction also, we let it run overnight because it has to run for a minimum of up to 3 hours. But due to time, we weren't able to let it run through just one day. So we let it run through overnight. And so what happened was this oxygen broke off and it bonded to the nickel, allowing this carbon to bond to this oxygen, and then the nickel bonded to the carbon here because it's double bonded. And then, so this is the ideal color of the isoxazoline that we were looking for when we were doing the reaction. When we were doing this, this is what we were looking for as when we continued on. And so we knew if we got this color, then it would be pure enough to be the actual isoxazoline.
So that was the first isoxazoline we made, and the second one uses palladium as a catalyst. So we took that oxime that we had made previously, reacted it with palladium 2 chloride this time instead of nickel 2 chloride. And we kept that copper 2 chloride there so it could oxidize the palladium and basically do the same thing that it did to the nickel, keep it from slipping into palladium 3 or back down to palladium 1, so it kept that charge so it could be reactively full. We also used methanol as a solvent again. That formed this palladium catalyzed isoxazoline. And you can notice this part in the bracket is exactly the same as the nickel isoxazoline. So this reaction, as with the nickel catalyzed reaction, had to be an anhydrous. So we made sure all of our compounds were anhydrous, all of our equipment was nice and dry, and there was no water that could get into the reaction and potentially break down the product. The reaction also had to run overnight so it could run to completion and fully form that isoxazoline. And it did essentially the same thing with the nickel. It took this partially formed ring and completed it over here, and the palladium was added on. You can notice also the color should be the same for both reactions, so that's the general color we were looking for the isoxazoline.
So product analysis. So as we were doing this, we had two methods of detecting whether or not our solution was pure enough to continue on with throughout. The first one is the proton NMR, which stands for nuclear magnetic resonance. And basically, what that did is it displays a structure of hydrogens in the molecule on a graph by using magnets to detect the hydrogens in the molecule. And when we did this, we used the solvent chloroform B, and what that does is dilute the solution that we have. So the test tube wasn't completely full of GNR acetylene, so we had some later if we needed to do further testing or purify it more. And then we also did the PLC plate, which stands for thin layer chromatography plate, which is basically a little piece of glass with a thin layer of UV light silica gel on top. And so what this does is it separates based off the polarity of the different molecules' polarity. And so if something was less polar, it would travel further up the plate, and if something was more polar, it would not travel as far as the other one did. And when we did this, we used the solvent 80 to 20 hexane ethyl acetate, and what that does is it allows the solutions to travel up the plate because it can't just do it dry. And so here we have a picture of the NMR, and this is just basically the barrel of the magnet. And we would stick our test tubes in the top, and then they would run the test. And then they're not in the picture, but over here there's it's supposed to be a little box, or it's a pretty good test box. And what it does is it computes all the data from the magnets and stuff, and it gives it the information. And then here we have a picture of the PLC plate, and you can see this one is less polar because it travels further out the plate compared to the other two. However, it's not as pure because all was left behind, and that's what this little area here is. And so these first four test tubes were more pure because they just moved up in the little dots that were the dots themselves moved up the plate cleanly instead of leaving a trail behind.
And so for our Grignard reaction, we had about a 60% yield, which was kind of low. For most of these reactions, we are looking for around an 85% yield, preferably higher. Except for the last two cyclization reactions. Those had a bit lower yield. And the way we calculated this was we took our actual yield, so what we actually got out of the reaction, which in this case was around 0.8 grams of that alcohol, and divided it by our theoretical yield, which told us that we had gotten more around 1.3 grams of the alcohol. And we multiplied that by 100 to get us the percent. And this is a proton NMR of that alcohol we made through the Grignard reaction. And as you can see, these different peaks correspond to different places on that line structure for the alcohol. And we use this proton NMR to basically verify that what we had actually made was the alcohol. And this is the TLC plate we took. We compared the PNS aldehyde, which was our starting material for the Grignard reaction, to the alcohol that was made after, which is this longer strand here. And as you can see, because the alcohol traveled up farther, up the plate farther, it was less polar than the PNS aldehyde. And we basically used this to, again, verify that we had made something through the reaction.
So the results of the activation reaction, we got 75% yield, so it's not relatively low. We wanted something higher if we were doing this, but it was okay. And then the math for the calculation of the day is actual theoretical cycle method, and we got our percent yield. And so here we have an NMR of the ketone, and you can see a lot of these peaks match up with the different carbons and stuff throughout the molecule, which indicated that it was pure enough to continue on with. And this allowed us, this indicated that we were able to make an oxygen. And then we have a TLC plate here comparing alcohol from the left over here and the ketone. And with this, the ketone was less polar than the alcohol, which indicated that it had more of the structure we wanted because that structure is less polar than the alcohol. But there was a little bit of solvent left behind, and that was kind of affecting our perspective.
And for the oxygen, we had the highest percent yield for the oxygen, getting around about 86% yield, which was better than the other ones. And it's still fair, but not as high as we would have liked it. And the calculation was the same as we did for the other ones. And this is the proton NMR we took of the oxy. And this proton NMR showed that, again, with these different places on the line structure, corresponding to the peaks of the graph on the NMR showed us that what we had made was actually the oxime that we wanted, and it also showed that we had made it fairly purely. And you can see there's a couple little other peaks here, and that's probably solvent and some other things. This one is probably our solvent that we actually used for the NMR, that chloroform B. And then this was the TLC plate. For the TLC plate, we compared the alcohol that we made in the first reaction, the ketone we made in the second reaction, and then this oxime we made in the third reaction. And it showed us that alcohol was the most polar out of all of them, so it didn't travel up the plate far enough. This ketone was the least polar because you can see there's still some over here, so it traveled up the plate a lot farther than the alcohol and the oxime. And then the oxime was kind of somewhere in between in terms of polarity.
And so for the nickel catalyzed glycosylation, we got a 72% yield. And that's still relatively low. And partially that was not actually what we wanted. And we did some calculation. We did the actual over theoretical, multiplied by, and then we got the 72% yield. And then here we had an NMR of the isocycline that was catalyzed to nickel. And so you can see here the isocycline formed, and the nickel bonded to it. However, it is in brackets because that indicates that the nickel breaks off and comes back on, and that's partially where the isocycline. That's why it was appears we would like it to be, because the nickel doesn't necessarily hold it as well as it's not strong, so it breaks off and it reforms again. And then a good indication that we did that that material is because of this ring on these little sphere peaks indicating that the ring is formed.
And for the palladium, well, we had our lowest percent yield for this reaction, only about 44%. However, on the NMR, we can see that it was actually more promising than the nickel, because these are the sphere peaks blown up. You can actually see they're more symmetrical than the ones on the nickel, and that actually shows in more detail that isoxanes are in there. So, though we did have a low percent yield, we actually made it in a fairly pure form.
So there was a number of possibilities that we didn't necessarily get as high yield from stuff that we wanted. One being the reactants were not ideal for the nickel cyclization because as we were doing this, it was more palladium based. Another being that the derivatives of the nickel and the palladium aren't necessarily strong enough to hold the isoxazyl ring. So they can be formed, but they only can hold it for so long, and then they break off again and reform, kind of like I was saying. And then the skill level of the researchers. We started off, we were amateurs more when we started off, so that kind of was an issue. But as we progressed on and got continued throughout the experiment, we were able to get better, and we had our lab techniques improved, and we were able to get higher percent yield as we went further. And then, of course, in the calculations of human error, that's always a possibility, just miswriting a wrong unit or something in the conversion, that's the numbers.
And with the nickel, the NMR, as we were kind of talking about earlier, the NMR showed that we didn't really make the nickel in a pure form. We made some of it, but not a lot of it. And this could be for a number of reasons. It could be because the conditions that we used for the reaction were not ideal for the nickel, and they might have been more ideal for the palladium. The nickel also might not have been oxidized fully, and that could be due to some impurities with our oxime that we used as the starting material, causing the copper to be unable to oxidize the nickel fully. And then, as what Dylan was saying, it could have also had some error along the way.
So, what happened with the palladium? So the NMR showed that the palladium was more greater than the nickel. There's a couple of reasons that could be. One being, like I said, the reaction that we did was more ideal for the palladium, which means like the conditions and stuff we used were meant to be cyclized with the palladium. Palladium is better than nickel at cyclizing because it's a stronger metalloid, and then it might already have a stronger metalloid. So it allows isocycline to form stronger and bond longer. And
we predict that there's going to be a lot more research conducted on the palladium and on the nickel as well. This is because we don't actually have a lot of research on the nickel right now, which is why we don't know the ideal conditions for it to be reacted under. And so that research will be geared towards discovering the right conditions for that nickel catalyzed reaction. The palladium will also have a lot more research conducted on it as well, because we already kind of know what conditions are right for the reaction. And we also know that the palladium works well at forming that isoxazoline. And of course, all this research will be geared toward making isoxazolines as a drug that can treat diabetes and cancer and all those inflammatory diseases that are caused by
why did you choose to do an HMR rather than like an IR, which would have been probably faster and cheaper?
Well, we just chose the HMR because we wanted a more precise reading. The IR does a fairly good job of showing that the structure's there, but we were also more familiar with the HMR, and it was also more detailed to show us exactly what we had made. And also then we could also see like the solvents and stuff. Because if we had solvents with the product, if the IR might have been a lot more messier than we wanted. Scott?
What number were you comparing your percent yields to figure out if they were high or low?
So the question was what number we were comparing our percent yields to figure out if they were high or low. And generally the numbers we got from the previous research suggested that we should have, like especially for the Grignard reaction, which we had about 60% on. The research suggests that we should have gotten actually into the 90s percentile range for that reaction. And so yeah, we basically just looked at the previous research to see if our percent yields were high or low compared to those numbers. And,
so you said earlier part of your goals were to reduce the cost to simplify the isoxazolines. So you can talk a little bit more about how you manage that.
So the question was, because our goal was to synthesize isoxazolines at a relatively low cost, the question was if we actually did that. Is that correct? And so we did because of that copper-2 chloride, since it oxidized those metals that we used. That's where most of the expense comes from, is those metals that we had used to catalyze the reactions. And since we oxidized those with the copper-2, we were able to use really low amounts. So for the nickel, for example, we used about 5% nickel-2 chloride and 300% copper-2 chloride. So we were able to use those in really low amounts because that copper oxidized it and it all be reacted.
Talk about variables and stuff. So, so what are variables that you think you will exclude from exclude interest in chemistry positions to begin with improve things? And what are the variables that you will include in the future to help you see what you have?
Okay, so is it what variables would we include next time and not include next time?
Yeah.
Yeah? Okay, so, okay. Just if variables we would include next time would be a lot of, like, for the ketone reaction we used, we used pyridinium chlorochlorate and magnesium sulfate and dichlorophane. So the reactions that start off, so that like those solvent or products we would use, so they would be the ones we would keep. And then so for some of the variables we would change would be the metalloids, so like the copper-2 chloride and the nickel-2 chloride. That's what was kind of experimented here. That's what we would change next time. So like we did with the nickel-2 chloride as well as the palladium-2 chloride. And so we would change the different metalloids to see which one would form the isoxazoline best and hold it the longest. So we would have a stronger, more pure isoxazoline, as well as one that would hold for longer. Maddie?
And how fast were the reactions like how long did it
For all of it, or just?
well, like,
Okay, so the reaction times that we took, so for the Grignard reaction, that one took about an hour and a half. But overall, the whole reaction test, everything took about the whole time, so about 4 hours, because it took kind of, we had to mask everything, all of our products and stuff. We had to make sure our, we had to usually put like round bottoms, we had to put them in the oven and let them dry for at least 5 minutes, and that was a good indication that they were dry. We also had to do calculations for our masses and stuff, and so that took some time. For the ketone reaction, or the oxidation reaction, that one also took about an hour to an hour and a half. We let the reaction run for 30 to 45 minutes because there was also some prep and stuff. And then with that, we had to add like the PCC, or like magnesium sulfate, they was kind of added at once, but like before we had the calculations, we had to make sure everything was dry and anhydrous and stuff. As far as the oxidation reaction goes, that one was, that one was a quicker reaction. It took like 30 minutes, about 30 minutes. To run through. We did it under heat and stuff, and so when we used like the Variac and setup to get the Variac set up for the heat, that took some time as well as like before calculations, and that was just kind of a general thing. So it took about 4 hours for that one too. And then the oxidation was ran overnight. But we also, there's a couple times we had to dry out we had to make sure the nickel and hydrous as well as the potassium chloride, so that they were in the oven for a while too. Just kind of like a few hours each time.